Let's talk some more about these closure properties, right? Last time we discussed complements and intersection. I said we also wanted to talk about the unions. Actually, the unions can be handled in basically the same way as the intersections, but so it's not going to be another sort of big deal about the unions, but let's just talk about the unions. So what about union? L1, union L2. The union, like I said, will be similar to intersections. So let me just refresh our memories. For L1 intersect L2, we use what's called the product machine, or the book calls this the product construction, because you build this new machine as a product of the states from the original two machines that you start with, right? The states in the product are pairs of states from one machine paired up with the states from the other machine. That's how you do the intersection. And the accepting states, really the only difference for the union is the set of accepting states. So for these two machines, I will write the tuples just once. We're not going to get, like I said, this does not require the amount of detail that we did last time. But we had the first machine look like that, and the second one was, I believe I called this R, delta 2, R0, and F2, right? So the only thing that you need to modify for the union is the set of accepting states. And I will just refresh our memory. For the intersection, L1 intersect L2, the accepting states in the product should be if you recall, we used F1 cross F2. Now, why is that? It's because F1 cross F2 means the set of all pairs where the first thing is in F1 and the second thing is in F2, right? And so if you end up in a state where the first thing is in F1 and the second thing is in F2, then that means this thing was accepted on the first one and also accepted on the second one. That's why we use the product here, because it gives you things which are accepted on the first and things on the second. All right? To do the union, instead, we need things which are accepted on the first one or on the second one. Now, it's a little less convenient to write that. This product means pairs where the first thing is in here and the second thing is in here. In your set theory discrete math class, actually you probably didn't talk about, is there some kind of operation where it's pairs but using or instead of and? Pairs where the first thing is in the first one or the second thing is in the second one. That's what we need here. There isn't actually a traditional set theory operation for that. But I will tell you what we need. For L1 union L2, we want to use, okay, it's going to be pairs where the first thing is in F1 or where the second thing is in F2, right? But it's or rather than and. You have to write this as a union of two things, and it's going to look like this. F1 cross R. This looks a little crazy. I'll try to explain. Q cross F2. This is what you have to do in order to get something like an OR in a product. So your interpretation of this means the first one is accepting. The second is anything, right? These are pairs in which the first element in the pair is in the accepting state from the first machine, but then the second can just be anything. Remember, R was the set of all states from the second machine. So this means accepting, this is pairs, which are accepting, comma, whatever, right? This R is just any possible state from the second machine. And then, of course, so this union means or, right? That's what the union sign means. And then the second bit here, this means the first is anything, that's the Q, and the second is accepting. So this is how, in set theory, we create the set of pairs where the first one is accepting or the second one is accepting. You have to break it down in 2 parts. Either the first one is accepting and we don't care about the second one, or the second one is accepting and we don't care about the first one. All right? This is how we get the union set. All right, so, but otherwise the whole thing is the same. So I'm just gonna, I don't think we need to go through the whole proof, but I will just say the product machine to get L1 union L2 is M, I'll call it, did I call it last time? N maybe? You go Q cross R, the whole alphabet sigma, the transition delta, the pair Q0, comma R0. This is all the same as the product machine from last time. But then right here is the only difference. F1 cross R union Q cross F2. All right. This is the formal description of the machine which gets you the union of the 2 languages rather than the intersection. All right. And I think that's all I want to say about this. So I will write the theorem. What we've done is, I mean, we've basically discussed the proof of this theorem. We're not going to write a proof because it's all the same stuff that I just said. But the theorem just says if L1 and L2 are regular, then L1 union L2 is regular. In other words, the regular languages are closed under unions. That's what we just demonstrated. All right. Are there any questions about that? This is just finishing up what we were talking about last time. And then the rest of today, we're going to move on to something else. All right. Great. Let's talk about something else. I thought we might, we should really, before we move on to something completely different, we should talk about an example of a language which is not regular. We haven't actually discussed that yet, really. Not a specific example, at least. Remember, regular means you can actually do this language using a DFA. What about something which is not regular? Let's just talk about a non-regular language. I mentioned this before, that if you want to show that something is regular, you just have to make a DFA which accepts that language. That's, I mean, we've done that on the homework. We've done many examples. If you want to show something is not regular, it means somehow you need to demonstrate that no possible DFA could ever accept this language. And this is much harder because you have to try to imagine any possible DFA and demonstrate that it does or does not have this language. That's why we haven't done any specific examples yet, but we've done enough. I wanted to do one example just as sort of as an example of how difficult it is to show that something is not a regular language. So here is one example, and actually this is sort of the example that you should always have in your mind, is this. This is not a regular language. If someone, approaches you on the street or in the club and asks you what your favorite non-regular language is, this should be your answer. This is like the classic example of a language which is not regular. And it's not even all that weird. It's just A to the N followed by B to the N. Those N's are the same, right? So this means that it has some number of A's followed by the same number of B's. This does not seem, to me, does not seem very complicated as far as what these are. I mean, you can write the elements very easily. The empty string, A, B, A, B, B, right? These are the elements of this. A, B, 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 etc. It turns out no DFA can have this as its language. This, to me, is a little surprising just because this is not all that weird. And it seems like, I don't know, if I asked you, if this was a homework problem, give me a DFA which accepts this language, you'd probably try to do it. You wouldn't immediately say, no, that can't possibly be possible. But it turns out it is impossible. So I want to try to demonstrate. So we'll have to argue that no DFA can accept this language. All right? And it has to do with the fact that this n is the same n both times, all right? In order to tell whether or not a string is in this language, the DFA would have to read a bunch of A's and then read a bunch of B's where it's reading the same amount of B's as it did with the A's. And a DFA, in order to do this, it would have to somehow read all these A's and remember how many there were, and then read these B's and somehow remember that there were the same number of B's as there were A's, right? And this is something that's hard for a DFA to do. In fact, it is impossible. I'm going to try to convince you that it really is impossible. We're going to kind of do this by contradiction. You imagine that there was a DFA which could have this as the language, and then you show that actually there's something wrong with that. So let's say, I'm going to say, for the sake of a contradiction, that's what this means. It means I'm going to make an assumption which I know is going to be false, but this is in order to generate a contradiction. This means for the sake of a contradiction, I'm going to assume M has this as its language, A to the N, B to the N, as its language. I hope you'll tell me if I go off the screen. What I see on my screen is slightly different from that screen because of the aspect ratio is different. I'm going to assume that M has this as its language. Now, and what I would like to do is let's imagine or let's think about what in the set theory language we would call this. A to the power, I'll say I, for various I. What I mean is, you got to start in the starting state, of course, but I'm just trying to think about what will it look like when you do various powers of A. You start in the starting state and you do a bunch of A's. Where does it end up after you do that? Now, I have no idea what the DFA looks like. This is a hypothetical DFA, but it's got to go somewhere if you start in the starting state and then do A a bunch of times, right? So I would like to think about these for various different I's, and it's a fact about a DFA, there are only finitely many states, right? This is part of the definition of a DFA. There are only finitely many states. Hold on, man. I'm having a hard time writing here. There are only finitely many states. That's what the F in DFA means. And what that means is these guys here, for various I's, they must repeat after a while. Like some of them must equal one another. When you start in the starting state and just do A over and over again, eventually it'll have to revisit one of the states it already visited. That's because there's only finitely many states. So you can't just keep on going somewhere new every single time, right? So that means there are only finitely many states. So look at that red comma. That's a special Stag's comma. There are only finitely many states, so eventually we'll get delta star of Q0 AI equals delta star of Q0 comma AJ. There has to be some two different powers of A that end up at the same state. That's because there's only finitely many, so you can't just get a new state every time. It has to repeat after a while, all right? Okay, but then, what if we follow this with B to the I, all right? Oh, let me just, for emphasis, I'm saying this must be true when I is not J, right? I'm just saying there has to be two different powers of A which land you at the same state. All right, I and J are not the same. I and J are different. Then, what if we were to follow this with BI? Okay, we get delta star of Q0 AI followed by BI, right? But because we started in the same place, this will also equal delta star of Q0 and AI followed by AJ followed by b to the I. I took each of these two strings and just stuck b to the I on the end of them. And since these match up at this state, you follow it with a bunch of b's, they have to match up still after b to the I. All right? Are you into this? I don't know. We're almost done. So it's okay if you're not into this. What can you say now about these things? This one right here, check it out. Here's the contradiction immediately. I would like to look at either side of this and ask, is this accepted or not by this machine? On the left side, I have a to the I, b to the I. Is that accepted? Yeah, remember the language was supposed to be this, a to the n, b to the n, right? So if the powers are equal, it's accepted. If the powers are not equal, it's rejected. So what we see here is this is an accepting state because the powers are equal. But this one over here is not an accepting state because the powers are not equal. Right? I have a to the j, b to the I, and I said before I and j are different. And this is the contradiction, right? Because these are supposed to be the same. They have to be the same state. But I said, on the one hand, this is an accepting state, but on the other hand, this is not an accepting state. And so that is our contradiction. The fact that these two things are different, this is our contradiction. Contradiction. All right? So it means our original assumption must have been false, which is to say, so there can be no such no such machine, M, whose language is A to the N, B to the N. All right? This is our conclusion. There is no DFA whose language is A to the N followed by B to the N. All right? So 2 reasons I wanted to go through this example. The first is just to convince you that, yeah, there is such a thing as a language which is not regular. We haven't had any examples yet of that, but this is an example. And second of all, just to demonstrate how difficult it is to show such an example, right? And the argument that I used here is not a general purpose argument. Like, if I give you a slightly different example, you would have to come up with a completely different proof, like per example. And we're actually going to learn in a little while, a couple weeks, a general purpose kind of strategy for showing that something is or is not a regular language. In particular, that is not is the more interesting part. But for now, I just want to leave you with that one somewhat weird example, and it's not easy. You have to do these weird proofs. We will eventually talk about a better way to do it than this proof. But any thoughts about that one? This is all I want to say for now about non-regular languages. This will be a major topic to come back to. All right, excellent. Okay, so can I just say the capabilities of DFAs are limited. That's because there is such a thing as not regular languages. The capabilities of DFAs are limited. There are some languages which are not regular. What that means is they cannot be the language of a DFA. In particular, even some simple ones like A to the N followed by B to the N it's not possible to make this the language of a DFA. So we are going to talk about other types of machines, at least, for 3 or 4 other ones over the course of the semester. And I want to talk about a new kind of machine, another type of machine which has more capabilities than a DFA, like it can do more stuff. There are more steps that it can do, or different steps. And it's called the NFA. The F and the A are the same, but the N is different from the B. Another machine, the NFA. So what this stands for is non-deterministic finite automata. Automaton. So DFA stands for deterministic. finite automaton. NFA stands for non-deterministic finite automaton. And it's like a DFA, only it's not deterministic. And remember what the word deterministic meant was that basically the machine has no random steps to it, or another way of saying that is that when you give it a particular string, it's going to do the same thing every time. It doesn't ever rely on some kind of chance or any other randomness. Anyway, what's different about the NFA? I'll say it this way. In an NFA, the same string can have different possible outcomes. I'll say the same string can lead to more than one path through the machine. The DFA is deterministic because there's only one way to go each time. You know, you have an A or a B, and you follow whichever arrow is appropriate. The NFA has some kind of like ambiguity in the arrows. There's some different possible options that you could do. You could go this way, or you could go this way. Here's what I mean. Here's an example. And you're going to have to kind of train your mind a little differently to get comfortable. I hope you feel fairly comfortable with DFA so far. Although I'm here to wreck your comfort by making you understand a new type of machine. Here is an example of an NFA. This is not a DFA. Can anybody looking at this, can you tell me why is this not a legal DFA? It's not. Yeah, what do you think? Yeah, right. From the state on the left, there are two outgoing B arrows, aren't there? I think there are. I think otherwise this is a DFA. Like that's the only place where this is different. So what's different about a DFA here? I'll say here, there's two different outgoing B's. All right? And so if I start with, if I gave these states names just for the moment, if I call them Q0, Q1 as two different states, here if we do the string A, B, we could end in state Q0 if you just did A, B both on this loopy edge, A and then B, or you could end in state in the other state. Or we could end in state Q1. That is, if we did the first A on this loop and then a B going across this way, right? It could end either way. This is how NFAs work. And we say, what then? You might wonder, what does it even mean for a string to be accepted? If it could be both, like it could be either one. We say the string is accepted if string is accepted if any of the possible states that you end up in is an accepting state. If any of the possible final states are accepting. So on an NFA, accepting means there is some path from the starting state to the accepting state when you read this word or this string. And a rejected word, or a rejected string would mean one in which there is no way to get to an accepting state if you're reading that string. Okay, this is what it means to be accepted on an NFA. So in this particular example, here in this example, AB is accepted because you can get to the accepting state if you start in the starting state and do AB. What do you think about AA? Is that accepted or rejected? He says rejected. Yeah, why is that?
Because the A can't leave the first state.
Yeah, if you start here and do AA, there's only one choice to do A. You have to do this, and then you have to do this again. So the AA from the starting state will be rejected. There's no way to get to the accepting state. this is how an NFA works. Any thoughts about this one? So we need to kind of, like I said, you got to sort of retrain your mind to look at a diagram and decide what kinds of things are accepted, what kinds of things are not accepted. And I don't know about that example. I don't know if it's clear. I got another example which is a little easier maybe to think about. How about this? This is a legal NFA. So in an NFA, each state can have any number of outgoing arrows. And I will say parenthetically, even 0 outgoing arrows. In this example, this state on the right here has no outgoing arrows. That is allowed in an NFA. All right. Each state can have any number of outgoing arrows. What do you think? Anyone want to try to say, just in plain words, what strings will be accepted on this machine, this NFA? You have to think about anything which can lead to the acceptance state. Yeah. Any string that ends in B. I like that. The way that I think of this NFA is you start here, right? And then you can do whatever you want as long as you like. Keep going back and forth with A's or B's. In order to get the accepting state, you got to do a B at the end. That's all. And then you can't do anything from here. You got to just sort of stop. So this accepts any string ending with a B. All right? Excellent. And it rejects, everything else. Rejects all others. In my opinion, actually, once you get used to these things, I think working with NFA is a little easier than with DFA, but you'll have to decide for yourself which one you like better. Yeah, great. Are there any questions about that example there? In many cases, if I just give you a language, it's often easier to write the NFA than it is to write a DFA for the same language. Anyone think you could come up with the, how about an NFA which accepts only strings starting with B? An NFA accepting any string starting with B. Start wing. I wrote start wing with B. Have we got an idea? That one that you still see there is anything that ends with a B. How about anything that starts with B? Yeah.
The initial state will just have an outgoing
Uh-huh.
arrow, and then the other one will be state, and then it will have a loop with a B.
Awesome. Yeah, this is what you want. I don't know. To me, it's a little easier to sort of visualize what this means. To me, it means you start here. If you want to get to the acceptance state, you better do a B, and then after that, you can do whatever you want. I don't care anymore. You can just do A's and B's forever. All right. So this NFA says, in order to be accepted, you must begin with B, followed by anything. All right. Excellent. Yeah. Great. Generally speaking, NFA can be smaller than a DFA which does the same thing. So often a NFA is simpler. By simpler, I mean it uses fewer states than an equivalent DFA. For example, how about I would like the language of the strings where the second to last letter is A. All right? Can we do a machine that accepts strings where the second to last letter is A? This actually is not too easy to do with a DFA. I'm going to try and I believe this is the simplest way to do it with the DFA. You start somewhere. First of all, it doesn't matter if there are a bunch of B's. What you care about really is the A's. This state here would represent the A is last. And then if you do one more thing with the A, then A is second to last. I'm going to say it this way. If you have an A here, then the last letter is A, but there were previous B's, so this is not accepting. But then if you have another A, then the last two letters are AA, and it should be accepting. You could also do a B here and be accepting. I'm not making these big enough. This is an accepting state where the last two letters look like A followed by a B. And then you just have to think about, okay, from here, what does it happen if I do a B? If you had the last two letters were AA, and then you did B, then the last two letters will be AB. So this B arrow should be there. If the last two letters are A and you do an A, then still the last two letters are A. If you end with AB and you do a B, it should go all the way back here. If you end with AB and you do an A, it should go to there. Anyway, this is a hard example, so I'm not suggesting that you should have come up with this as fast as I just did on my own. But I'm just trying to say this is the kind of I think this is the simplest possible DFA for this language, where the second to last letter of the string is an A. It's not very easy in my opinion. But an NFA is considerably easier than this. So this is a DFA. What about the same language but on an NFA? Remember we did like this one here is any string which ends with a B, right? You can do something kind of like that where it has maybe it does whatever you want and then has an A and then has one more thing and then that's the end, right? That's what I want to write here. Maybe maybe I'll give you a moment here to see if you can write an NFA that acts like that. So my idea is do anything, then A, then one more letter, and then accept. All right? See if you can make an NFA that has that kind of behavior. This is the way that I would like to think about. Second to last letter being A. And when I did this, I did it in 3 states. See if you can do it with only 3 states. I'm going to walk around and see how you're doing. I hope you don't mind if I look at your paper. So this has a A and then another A. Second to last letter is A. Second to last letter is A. All right, I know I didn't talk to everybody. Let's see what we got. I saw several people gave me what I wanted. This, I think, is the best way to do this example. A comma B here. I hope you said something like that. So my interpretation is, at the beginning, when you start, you could do whatever you want for as long as you want. Then you got to do one A, and then one more something, and then that's the end. All right? Yeah. No, you don't. This is a good thing, and I mean, this is a good question, and somebody else brought this up. What about say something like A, B, B, B? Is this accepted or rejected? You will find yourself wondering. Okay, I could do A. Certainly, there are many ways that you could try to run through this string, right? You could just do them all right here. A, B, 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 and then it would be rejected, okay? But it's a little more interesting if you did something like A, B. You get here, and then you have two B's left over, but you're like stuck over here. This is why you might feel like, shouldn't there be another arrow so you don't get stuck? And the answer to the question is, no, you can just get stuck, and that means that it's rejected. So to say that the string is accepted means there is some way to read the whole string and end up in the accepting state. The fact is, there is no way to read this whole string and end up in the accepting state. Because if you get stuck after a while, then that doesn't count as ending up in the accepting state. Because you don't actually... Yeah, if there's nowhere to go, it means you didn't finish the string, and so it's not accepted. Yeah. Although I think in this example, probably if you did put an extra arrow going back, it's not gonna ruin your answer. Like, it's still a correct answer, but that arrow is not necessary. All right. Any other questions about that? That's a good question. Okay, one last thing. So the point of this little example here is just that it is often a lot easier to draw an NFA than a DFA for a particular language. If it's up to you to do a DFA or an NFA, often the NFA is simpler. Okay. One last capability, which I haven't gotten to about NFAs. NFA can also do what is called a spontaneous transition. Spontaneous transition. You know, spontaneous means sort of like all of a sudden without any warning. Spontaneous transition, that is, it can, this means a transition, like an arrow on the diagram, which consumes no letter in the string. All right? That is, without even reading one of the letters, there can be an arrow which happens without reading a letter. All right? This is, we're going to write it. Here's an example. A spontaneous transition on the diagram is written with an epsilon, you know, the empty string. Something like this. So what those epsilons mean is the machine can just go down one of those arrows without reading anything from the string. Those are called spontaneous transitions, or more often we're just going to call it epsilon transitions. All right? And so what does this mean? This accepts any string. The idea is you got to start here, but then even before you read anything from the string, you can just jump from one to one side or the other. And then over here, you can do a bunch of A's and accept. Over here, you can do a bunch of B's and accept. So what would this, can you say in words, what are the strings which are accepted by this one? Yeah.
It's either an empty string, a string of all A's, or a string of all B's.
Yeah, it's either all A's or all B's, or perhaps the empty string. All right. Any string, can I say, like, A to the n or B to the n, right? And this would include the empty string if the n is 0. It does not accept a string like AB, or some string with a mixture of A's and B's cannot be accepted by this NFA. All right? How about this? I got one little variation. Using some more epsilons here. How about this guy? What do you think about that? Does that make any difference if you put the epsilon in there? I think it does. This accepts any string like. Any thoughts? Yeah.
Any string A's and B's on the empty string.
With A's and B's? I don't think it's quite anything, any mixture of A's and B's. Like for instance, ABA, I think is not accepted here.
It has to end with a B.
I think ABAB is also not accepted here. Okay.
Either all A's or all B's, or A and then B. So
A and then a B?
followed by B, but no combination of them. So AAA, BBB.
Okay, yeah. So I think it is. If you just think about if you're like, you know, a gerbil living in this maze or something, you got to start here. You can go up here and do some A's, and then you can go down here and do some B's, but then you got to stop. There's nowhere else to go from there. So I think what he said, it's some number of A's followed by some number of B's. So that's it. You can't go back and do some more A's, right? So this would be accept any string like. How could I write that in terms of similar to this? Is there a simple way to say that? What do you think? Yeah, any string like A to the N, B to the M. So those are different N's and M's. Yeah. Excellent. Great. One last variation. What if same thing, but I'm just going to add another epsilon going back to the other guy. What do you think about that? So now if you're the gerbil, you can actually go back and forth here if you want to. What kinds of strings can you get now? Yeah. Let me see. So A to the N, B to the M, or B to the N, A to the M? Is that what you said? Yeah. I agree. All those things are accepted. Is there more stuff than that? Maybe. I think actually even more would be acceptable.
Is it just the alphabet and A, B?
Yeah, I think actually any string of A's and B's will be acceptable here. Like anything. If I did A, B, A, B, 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 A, B, can you do that? I think you can by going back and forth here. Whenever you want, you can do these epsilons back and forth. So I can go here, do the first A, then go down here, do the B, then go back up here, do the A, go back down here, do 3 B's, back up A, back down a B. Yeah, so this actually, I mean, these are acceptable, but this accepts, come on now, any string, you know, in A, B star, right? Any string involving A's and B's will be acceptable here. Excellent. Did I say that was the last one? I also wanted to do this. What if I just make like this? I put the epsilons kind of in a circle instead of however you want to describe what they were last time. Any thoughts? What is accepted on this guy? Yeah. And then it starts with an A. So you go here, you do an A, and then you can do whatever else you want. I think, do you have a need to start with an A? Yeah, I think you don't. If you started with a B, you could just go epsilon here and then epsilon here and start with your B, right? I think it's not, I think this still accepts anything, right? You can keep on just going around the circle here and do some A's or some B's whenever you want to, right? So this also accepts everything. All right, AB star. All right, these are NFAs.
So that one that we just drew rejected in here.
No, no string is rejected by this one. No.
So the one
And the previous one, yes. They accept everything, that means they reject nothing. Yes. No rejection. Okay, excellent. We got 3 more minutes. Let me just summarize here, and then we'll go on to something slightly different. So I'm going to say the NFA is the same as the DFA, but two important differences. First of all, we allow these epsilon transitions, which are not allowed in a DFA. We allow epsilon transitions. And second of all, the next thing I'm going to say is just that every state has, it can have any number of outgoing arrows. It doesn't have to just have one outgoing. But I'm going to say that in a more technical way here. We allow epsilon transitions, and for any state and letter delta of Q comma A, this is the transition. In a DFA, this equals a particular state. But in an NFA, it could equal many states, because there could be several outgoing arrows. Or it could equal no states at all. And so this is a set of states. This is the difference with a DFA. In a DFA, this was a specific state, one state that you get as the answer. But in an NFA, it could be any set, possibly empty. Maybe the empty set, right? It could be any set of states. That means there can be any number of outgoing arrows, perhaps 0 outgoing arrows. Could be the empty set. All right, I think that'll do it. Next time we're going to talk about the formal description of an NFA, just briefly. It's similar to the DFA. Do that homework. Good night. Bye-bye, Zoomers.
Thank you.
See ya.